Hi everyone, Dr. J here, and in this video I'm going to talk to you about model complexity and correctness and how those two things work together. So one of the things that Dr. Keres talks about in the textbook is that you can have very complicated models. We talked about this especially in the context of deterministic models, where you're trying to incorporate all of the relevant physics. You've got lots of parameters, lots of unknowns, lots of data, and you're trying to kind of make that all work together. Now that would be a very complex model which may or may not be able to capture the uncertainty in the model output because it's so complicated. So for example, global circulation models that are related to climate take many thousands of CPU hours to run, and so those models are you're not going to be able to do simulations with those models and generate hundreds or thousands of realizations, stochastic realizations, in order to build distributions on the parameters and look at the uncertainty in the outputs and things like that. You might get a few different outputs from maybe a few different types of models, but that's about it. And there's this idea in modeling of degrees of freedom. And I've actually got a setup here on the board where we've got some data, and we're going to try to model that data with two different models, or we might try to think about modeling this data with two different models. One of those models has 3 parameters, and one of the models has 30 parameters. So, for example, a 3-parameter model might be trying to fit a quadratic to some scatter plot data. So you've got a line plot would be slope times x plus intercept, so mx plus b. A quadratic would be a times x squared plus b times x plus c. So 3 parameters in that particular model. Whereas another model, you might have all kinds of different, for example, a physics-based model might have a number of different parameters relating to, in a reservoir model, for example, porosity, permeability, grain size, tortuosity, compaction level, density, the list goes on. You get the idea. The question is, which one of these two models is better? Which one of them is better to model the data with? We have some data. The data is the same. Data is not changing. But we have 2 possible ways to model that data. One thing to think about when we're building models, looking at how to model data, is that 2 models that fit the data equally well. Normally someone would say, if they kind of took a look at these 2 models and they said, well, both the models are actually fitting the data pretty well, pretty similarly. But this model has 30 parameters. Most people will reject this model in favor of a much simpler model. And Dr. Keres talks about this in the textbook and brings up this idea of Occam's razor, which is that we should use the simplest model possible to explain the observations. But there's something important to keep in mind here, which is something that my PhD advisor told me when I was in his research group, and that is that we're not here to fit data. The goal of a modeling exercise, and this includes modeling uncertainty, is not to fit the data. It's not to come up with a model that just fits the data that we have, but the goal of what we're doing is to understand something about the Earth or the Earth system that we're modeling, and that includes the component of the modeling that involves uncertainty. Now, as an example, if we're in building a reservoir model, the goal is not to fit the model, the data or the observations that we have. So that is a goal, one part of the goal, that our model needs to be calibrated to the data that we have, but that's not really the goal. The goal is to understand the system that we're modeling and try to be able to make realistic and reasonable predictions or forecasts based on our understanding, best possible understanding of the Earth system that we're looking at, this particular reservoir model. And this brings up another important point, which is the idea of model tuning or model calibration. You'll hear people talk about this. So you'll build a reservoir model, and then you'll calibrate it using a set of data, right? So for example, you might build a flow model or a production model and calibrate that with inputs such as pumping and outputs such as production. In a geotechnical model, you might build a model of the subsurface and calibrate it from borehole observations and geophysical measurement. Calibrating and tuning your model so that it matches the observations is not a bad thing to do. That's a good thing, and you have to do that in order to ensure that your models at least explaining the observations that you have. But it's actually not good enough. And the reason for that is simple. You have two models, both of which take data. These two models might, in some cases, have different physical implications or different implications for the Earth system that you're modeling, but they both fit the data equally well. And what might be the reason for that? Limited data. So model calibration and tuning is entirely 100% dependent on the data that you have. So if you don't have data, if your data are biased, for example, or if you haven't sampled all the parts of your reservoir, or if your sampling routine is such that you're only getting a particular subset of the relevant observations, it's not random in time and space. Any of those things can lead to model calibration, which matches the data. So you built a model, and again, as I said, you have these two models, they both match the data, but very different representations of the Earth system. And so the question is, which one is better? There might be good reasons, actually, for choosing a 30-parameter model if, as I said, you're incorporating physics that you think is reliable and reasonable to assume. On the other hand, if you're just trying to get very simple predictions or forecasts from the model, a 3-parameter model might be even better than a model, a 3-parameter statistical model, I should say, might be even better than a physics-based model, where you don't actually need to use all of the physics to get the output or the result or the prediction or the forecast or the decision that you really need to make based on the data that you have. If this sounds a little all nebulous to you and not really hard and fast, that's because it really is. There's a lot of decisions that have to be made with any modeling framework. When you're modeling your system, you're always going to have to make simplifications. Even the most complicated models are do not fully and truly represent your system. We just don't have data to do that. And especially the deeper you go in the subsurface. So for the shallow subsurface, you might be able to characterize it really well with geophysics. You might be able to drill a lot of boreholes, shallow boreholes. As you go deeper into the subsurface, things get more and more uncertain. Your resolution gets lower and lower, and that's going to be true no matter what you're doing or where you are. So there's always going to be trade-offs between having a more complex model that might actually fit the data a little better in some cases versus a simpler model, which is much easier to calculate, much easier to compute. You can run stochastic realizations easily with a 3-parameter model. You can do Monte Carlo simulation, whatever you want. That's not going to be a problem at all. But you're going to sacrifice something. And that is, you're going to sacrifice, perhaps, in some cases, a better physical understanding of the processes and the properties of the Earth system that you're modeling. And that's where a physics-based system where you've got actual realistic physics incorporated might be a better way to go. So this little mini lecture is just kind of like a cautionary note. Don't just assume because you're given a particular model that that's the best model to use for your Earth system. Don't just assume that a more complicated model is better than a simpler model, or vice versa. You need to really think about, again, what is the goal of what you're trying to do? Understanding the Earth system, understanding a particular forecast, for example, global temperature change over the next 50 years. What do you need to quantify? What uncertainties do you need to capture and quantify? What relevant physics do you need to capture and quantify in order to make the best possible prediction for what you need, or the best possible forecast, and be able to quantify the uncertainty in that forecast? It's not going to be an easy thing to do. You'll have to think about it, and you'll have to get expert opinion. Look at what the data is telling you. Sometimes the data itself can give you an indication of what type of a model is better one to use. But very often we're relying on expert opinion or our own background knowledge of what is the best type of model to use for a particular system. Okay, so with that, I will wrap up and see you in the next video.